You know, usually when we build something massive,
Right.
like a physical structure, a suspension bridge, or a 90-story skyscraper, we operate under this absolute expectation that the foundation is going to be solid.
Right.
Like,
Yeah.
we pour the concrete deep into the bedrock, we rivet the steel beams together, and once it's built, it's stable. I mean,
Yeah.
gravity is a known variable. The tensile strength of the materials, that's calculable and fixed.
Yeah, it's comforting because it's entirely deterministic. You calculate the load, you build the required physical support, and, well, the structure stands. We're biologically wired to like things that are visible, things that follow physical laws we can actually see and feel and inherently trust.
Exactly. But then we step to the world of large language models, these massive AI brains with hundreds of billions of parameters. We hear these numbers thrown around all the time, right? Like, oh, 70 billion parameters or a trillion parameters. But we rarely talk about the physical reality of what that actually means.
Yeah.
And suddenly, that concrete foundation we rely on in the physical world is just, well, it's completely gone. Because when you look at the actual source material, the dense technical papers driving today's AI, we're looking at an engineering landscape that is, honestly, it's terrifyingly fragile.
It really is. I mean, trying to balance a skyscraper on the tip of a needle during a hurricane that's probably the most accurate visualization of what is actually happening inside these data centers.
Wow. A needle in a hurricane.
Yeah, because when people use an LLM, they see a clean chat box that confidently types out a recipe or writes a poem. What they don't see is the underlying math actively warring against itself.
Right. So, welcome to the deep dive. Today we're taking you into a massive stack of incredibly dense technical research, right from the absolute cutting edge of AI development. And our mission today is to extract the most mind-bending insights from these papers.
Yeah, we're going to look at the hidden physics, really. The brutal engineering compromises and the downright bizarre mathematical paradoxes that allow large language models to actually work without, spontaneously self-destructing.
Because self-destruction is exactly what they naturally want to do.
Yeah, absolutely. Left to their own devices without incredibly strict architectural constraints, these neural networks they want to tear themselves apart mathematically.
Okay, let's unpack this. Because today's deep dive is based on a fascinating, highly technical breakdown of LLM architecture. We're focusing specifically on this concept called training stability and the unseen, frankly violent battles happening inside the neural network every single time it tries to learn a new word.
Right.
And there's this really common misconception out there that making an AI model bigger, simply going from billions to trillions of parameters, automatically makes it smarter. But according to the research, it actually makes it incredibly unstable.
It does. And AI researchers are constantly fighting this invisible mathematical force that is actively trying to erase the model's memory.
Wow.
Yeah, the central idea we're grappling with today is that training an LLM isn't just about feeding it a mountain of internet text and letting it read. It's an active, highly constrained, moment-to-moment fight against numerical chaos.
And we have to consider the stakes here for you listening. We're talking about training runs that cost millions, sometimes tens of millions of dollars. You have thousands of specialized GPUs running continuously for months on end.
Exactly. And in that environment, a single numerical error inside the matrix can't just be ignored. It can literally kill the entire project instantly.
Instantly. So before we can understand how the brilliant architects behind models like Meta's Llama or Google's Gemini actually fix these networks, we need to understand the failure states.
We need to know how they break. Yeah.
Right? We need to know what a collapsed skyscraper actually looks like in the AI world. So the sources talk a lot about stability. What does that word actually mean when we're just, staring at a screen full of code?
Well, when researchers talk about stability in the context of training, they're almost exclusively looking at one metric, and that's the loss function. You can think of the loss function simply as the mathematical measure of how wrong the model is at any given moment.
Okay.
When training begins, the model is essentially a baby. It outputs pure gibberish, so the loss is very high. Over time, as it processes more text and adjusts its internal weights, you want that loss to drop smoothly and predictably until the model converges on a solid understanding of language. So stability means that the loss curve goes down without catastrophic numerical anomalies.
Got it. It's like a teacher grading a student. Over the semester, the student's error rate should go down. But when stability fails, the research highlights 3 specific disasters that strike the network. Let's walk through those. What's the first disaster?
The first phenomenon is what the industry calls a loss spike. Picture the scenario. Your model has been training across a massive server farm for 3 weeks. The loss curve is charting downward beautifully. It's learning grammar, it's learning historical facts, it's starting to grasp logic.
Everything's going great.
Everything's great. And then at one specific training step, out of billions of steps, for absolutely no obvious reason, the loss suddenly skyrockets. It might jump from a value of 2.0 straight up to 10.0 or even higher.
So the student was getting straight A's, and then one morning wakes up and suddenly forgets how to speak English entirely.
That's a great way to put it. Sometimes, if the researchers are lucky, the model manages to self-correct. The optimizer realizes the error, makes drastic adjustments, and the loss comes back down after a few thousand steps.
Okay, so it can recover.
Sometimes. But very often, it diverges entirely. The loss spirals completely out of control, and everything the model learned over the last month of multi-million-dollar compute is just scrambled into total noise.
Just totally out of nowhere. I mean, that is terrifying from an investment perspective.
Yeah.
What causes a network to just lose its mind like that?
Well, often it's a precursor to the second disaster, which is widely considered the most fatal event in machine learning. It's the NaN or INF crash. Yeah, NaN stands for not a number, and INF stands for infinity. This occurs because of a very real hardware limitation known as numerical overflow.
Okay, let's unpack numerical overflow for a second. We're talking about computers trying to process numbers that are just physically too large for their memory banks, right?
Precisely. Deep neural networks function by performing billions of matrix multiplications every single second. If, at any point during those multiplications, an activation value inside the network or a gradient being passed backward becomes too large for the specific memory format the computer is using, the hardware basically throws its hands up.
It just quits.
Right. It cannot represent the number physically in its memory, so it defaults to the code for infinity or not a number.
It's like taking a standard desktop calculator, typing in the biggest number possible, and hitting multiply by 1,000,000,000. The screen just flashes error because it literally doesn't have enough digital real estate to show all the digits.
Exactly. And in a neural network, it doesn't just flash a warning and let you move on. That NaN value acts like a highly contagious, highly toxic virus.
Oh, man.
Because the neural network is fully connected. That means the next layer in the sequence is going to take its inputs and multiply them by that NaN value, and mathematically, anything multiplied by NaN becomes NaN.
So it just spreads.
Instantly. In a fraction of a second, as the calculations ripple through the forward and backward passes, that single NaN spreads through the entire matrix. The weights are overwritten with NaN, the gradients are destroyed, the entire training run undergoes sudden cardiac arrest.
A single bad number out of hundreds of billions, and the whole multi-million-dollar training run is just dead. There's no undo button.
I mean, you can load a saved checkpoint from a few days prior, but if you don't fix the underlying architectural flaw that caused the number to explode in the first place, it's just going to hit NaN again the exact second it reaches that same piece of data.
That is an absolute nightmare. Okay, so we have random memory wipes in the form of loss spikes, and we have toxic number viruses causing instant death. What's the third disaster?
The third disaster is a bit more insidious. It's the phenomenon of gradient explosion or gradient vanishing. To understand this, we have to look at how a model actually learns. It uses an algorithm called backpropagation.
Right.
When the model makes a mistake, an error signal, which we call the gradient, is calculated and sent backward from the output layer all the way to the first layer. This signal tells every single parameter how it needs to adjust itself to do better next time.
It's like a chain of communication. The final output tells the layer before it, hey, we were way too high, lower your values, and that layer passes the message back and so on.
Exactly. The problem arises as models get incredibly deep. We're talking about moving past 80, 90, or 100 layers. The mathematical reality of backpropagation relies on the chain rule from calculus, which essentially means those error signals are being multiplied by the weights of each layer as they travel backward.
Ah, I see where this is going. If you multiply a number by something just slightly larger than 1 over and over again, it's going to grow.
Exponentially. If the gradients are even slightly too large, they multiply across 80 layers into a massive explosion, completely shattering the model's weights and usually leading straight to that NaN crash we just talked about.
Right.
But the opposite is equally deadly. If the gradients are slightly less than 1, say 0.9, and you multiply 0.9 by itself 80 times.
It becomes microscopically small. It just shrinks down to basically 0.
Yes. The signal vanishes entirely. The deep layers of the network, the foundational layers near the input, they receive an error signal of 0. They are essentially being told, everything is perfectly fine, don't change anything.
Wow.
So those deep layers just freeze in place. They become completely unable to learn any new features, while the top layers frantically try to compensate for everything. The model's capacity is totally crippled.
Okay, so we have the heart attack, the virus, and the slow freeze. But here's what I really want to know.
Yeah.
We've had neural networks for decades, right? Researchers were training models back in the 2010s. Why are these massive, large language models so uniquely fragile? Why are we suddenly dealing with a glass house?
It all comes down to the magnifying effect of extreme scale. We aren't dealing with million-parameter models playing chess anymore. When you scale up to trillions of parameters, any microscopic numerical disturbance is magnified by the sheer depth of the operations.
Okay.
Imagine the training data contains one single weird token, maybe a bizarre string of HTML from some scraped website. Or imagine the random number generator that initializes the weights on day 1 spits out a value that is just a fraction of a percent off balance.
Just a tiny anomaly.
Right. That tiny anomaly is passed through 80 layers of massive matrix multiplications. By the time it reaches the end, it has cascaded into a Category 5 numerical storm.
So it's the butterfly effect, but playing out inside a glass house. A butterfly flaps its wings in layer 1, and by layer 80, the entire skyscraper shatters.
That perfectly captures the fragility. And making things significantly worse is the fact that we're forced to build this glass house using compromised materials.
What do you mean, compromised materials?
Well, to train models this massive, you need an incredible amount of GPU memory. Standard computing uses a format called 32-bit floating point numbers, or FP32. This format is incredibly precise and can hold massive numbers, but FP32 takes up 32 bits of physical memory for every single parameter. When you have a trillion parameters, you simply cannot afford the physical memory or the massive energy required to compute in FP32.
So we have to shrink the numbers to fit them on the graphics cards.
We have to shrink the format. The industry shifted to mixed precision training, heavily relying on a 16-bit format called FP16. It cuts the memory requirement entirely in half, which is a massive cost saving.
Yeah.
But FP16 has a brutally narrow dynamic range.
How narrow?
In computer science, a floating point number has bits dedicated to the fraction or the decimal detail and bits dedicated to the exponent, which determines how big the overall number can get.
Like scientific notation. The 3.1 form part is the fraction, and the times 10 to the 5th part is the exponent.
Exactly. In FP16, the maximum value it can physically represent is roughly 65,504. Now, 65,000 seems like a decent number for an everyday spreadsheet, but in the context of a massive neural network where thousands of dimensions are being multiplied and summed together billions of times a second, hitting 65,504 is incredibly easy.
And the moment you hit that ceiling.
The moment your math exceeds that ceiling, you get an overflow, you trigger a NaN, and your model dies.
So we're trying to simulate the sheer complexity of human language, which requires massive mathematical representation. But we placed a hard physical ceiling at 65,000. It's no wonder the network keeps hitting its head.
Yeah.
How did they fix that specific limitation? Because they obviously didn't stop building bigger models.
The industry's savior was a new format developed by Google called bfloat16 or BF16. It is a brilliant piece of engineering compromise. It's still a 16-bit format, so it still saves the required memory, but it radically reallocates how those 16 bits are used.
Okay, what do they change?
It sacrifices the fraction, meaning it severely cuts off the long decimal tails of the numbers, making the math far less precise. But it takes those bits and gives them to the exponent. BF16 keeps the exact same exponent range as the massive 32-bit format.
Oh, wow. So instead of capping out at 65,000, how high can BF16 actually go?
BF16 can represent numbers up to 10 to the 38th power.
That is an unimaginably huge number. It's like giving up the ability to measure a millimeter perfectly just so you can measure the distance to the edge of the universe. We stopped caring if the number is exactly 3.141592 and just cared that we could hold numbers as massive as stars without the computer crashing.
That's spot on. It's the ultimate pragmatic trade-off. By giving up decimal precision, BF16 makes the model almost entirely immune to numerical overflow crashes.
But I'm guessing that wasn't the only fix.
No, hardware formats alone weren't enough. The architects had to fundamentally alter the blueprint of the neural network itself. Older transformers used a design called postnorm. In post-norm, the data would pass through a heavy mathematical layer, like attention, and then the normalization layer would be applied afterward.
Normalization is like a safety valve, right?
Yeah.
It scales the numbers back down to a manageable size.
Yes. But applying it after the transformation meant that as those error gradients flowed backward during learning, they bypassed the normalizers and accumulated directly in the main artery of the network. They got massive near the input layers, causing explosions. So the industry almost universally shifted to a pre-norm architecture.
Putting the safety valve at the front door.
Exactly. Specifically using a variant called RMS norm. By putting the normalizer before the complex math block, it ensures that no matter how deep the network is, the signal entering the layers is strictly controlled and suppressed before it can ever multiply into a storm.
Okay, so we've got our BF16 hardware armor to prevent the memory limits, and we move the normalization to the front door to act as a shield. We're really trying to control these numerical storms. But if we really want to understand why the glass house shatters, the sources indicate we have to look closely at the fundamental ingredients of the network itself.
We do.
And this brings us to one of the most surprising revelations in the research. There is one specific, incredibly toxic ingredient causing these storms. And it's something that literally every single person who takes an AI 101 class learns about on day one: the bias term.
Yes, the humble bias term. If you recall basic high school algebra, the equation for a straight line is y equals mx plus b. The m is the weight, the x is the input data, and the b is the bias.
Right, it's foundational.
In traditional machine learning, the bias is essential. It provides the ability to shift an activation function left or right. It increases the expressive space of the model, allowing it to fit data that doesn't perfectly cross through the zero origin.
But the research points out a totally wild fact. If you go on GitHub right now and dig into the open source code for modern, state-of-the-art models like Meta's Llama 3, Google's PaLM, or Gemma, you will find something bizarre. Almost all of their linear layers, their attention projections, their normalization layers, they explicitly feature a single hard-coded line: bias.
False.
They intentionally rip the bias term out of the math entirely.
They do. It seems super counterintuitive to remove a tool that gives the model more flexibility. But in a multi-billion parameter transformer, the bias term transforms from a helpful algebraic tool into a silent, systematic killer of training stability. It is incredibly toxic at scale.
Wow.
The research papers break this down into 4 distinct mathematical reasons why the bias absolutely has to go.
Let's go through them. Why does a basic high school math concept destroy a trillion-dollar AI?
The first reason deals with a phenomenon called mean shift in the residual stream. We need to visualize the architecture of a transformer. It's built on a residual stream which acts like a central highway flowing from layer 1 all the way to layer 80. Each layer is like an off-ramp. It takes some data from the highway, processes it, and then adds its new insight back onto the highway.
So it's an additive process. Layer 20 takes the sum of everything before it, calculates something new, and adds it to the total.
Right. Now, consider what a bias term actually is. It's a constant vector of numbers. It does not depend on the input text. Whether the user types hello or quantum mechanics, the bias term added at layer 10 is the exact same constant value.
Okay.
Over 80 layers, these constant vectors linearly accumulate. If layer 1 adds a small bias of 0.1, and layer 2 adds 0.1, and layer 3 adds 0.1, by layer 80, you have a massive, unavoidable constant shift in your numbers. The abscent mean of your network's activations drifts violently away from zero.
Okay, I want to make sure I'm visualizing this correctly. Let's take a shopping cart analogy. Having a bias term in a shallow network is like pushing a shopping cart that has one busted wheel that constantly pulls slightly to the right.
Okay, like that.
If you're just walking 10 feet down a grocery aisle, it's totally fine. You adjust your grip, you barely notice it. That's a traditional neural network. But a large language model is like taking that exact same broken shopping cart and trying to push it down an 80-mile highway. Over 80 layers, that tiny constant rightward pull accumulates unconditionally. And eventually you end up careening completely off the road and crashing into a ditch.
That is a phenomenal way to visualize it. It causes systemic covariate shift. By the time the data reaches the deep layers, it has drifted so far from the center that the optimization difficulty becomes immense, leading directly to those loss spikes we discussed earlier.
So that's the first reason. What's the second?
Now, the second reason bias is lethal is intrinsically tied to how it conflicts with modern safety mechanisms, specifically RMS norm.
Right, RMS norm. We mentioned it earlier as the shield at the front door. Root mean square normalization. How does the bias fight against the shield?
To understand the conflict, we have to contrast it with older normalization. Older models use layer norm. Layer norm did two things. First, it calculated the mean of the incoming data and subtracted that mean to perfectly center everything back at zero. Then, it divided by the standard deviation to keep the scale tight.
Okay, that sounds pretty safe.
It is, but calculating and subtracting the mean across billions of parameters is computationally expensive. It slows down the training significantly.
And in AI, speed is money.
Exactly. So RMS Storm acts as a speed hack. It skips subtracting the mean entirely. It just takes the data and divides it by the root mean square. It operates on the strict mathematical assumption that the data is already roughly centered around zero.
Ah, but if we left the bias term in,
Then the assumption is broken. If the bias term has caused that massive shopping cart drift, your data has a huge constant offset. Let's call that offset a massive constant C. When RMS norm goes to calculate its denominator, that massive constant C gets squared and it completely dominates the calculation.
wait, so the denominator just blows up?
Yes. The denominator becomes artificially huge, not because of the actual words being processed, but just because of the accumulated bias drift.
So when RMS norm performs its final division step, it's dividing by a massive bloated number.
Precisely. And when you divide by a massive number, the output gets incredibly small. RMS norm violently crushes the actual dynamic signal, the delicate mathematical variations that actually represent the word cat, or the grammar of a sentence.
Oh, wow.
The semantic signal is heavily attenuated, suppressed by the giant bias, leading directly to the gradient vanishing problem. The model literally goes mathematically numb.
So the bias pulls the cart off the road, and when the safety system activates to fix the drift, the math works out in such a way that the safety system just crushes the actual cargo inside the cart. That's a brutal conflict. That's two, was the third reason. The third is a physiological issue for the network, dealing with dead neurons. Modern LLMs use advanced activation functions, primarily SWIGELU, or sometimes GELU. These functions have a very specific geometric shape. On the right side, for positive numbers and numbers near zero, they're highly active. They allow gradients to flow, which means learning is happening.
Okay.
But on the far left side, for large negative numbers, the function flatlines. It outputs a hard zero. We call this the dead zone.
If a value hits the dead zone, what happens to the neuron?
If a neuron's activation falls deep into that flat line, its output becomes zero, its local gradient becomes zero, and it permanently stops updating. It becomes a dead wire in the brain.
Now remember that the bias is a constant number added indiscriminately to every single token. If the optimizer badly initializes the bias or violently updates it in the wrong direction during a step, that bias acts like a constant, unyielding bulldozer. It can physically shove the entire distribution of activations deep into that negative dead zone.
It just pushes the math into a brick wall.
And suddenly, a huge percentage of your network's capacity is shoved into the flat line. The model just halts learning. And if the optimizer realizes the mistake and manages to forcefully yank the bias back into the positive zone, you get massive gradient oscillation. It's chaotic, jittery, and entirely destabilizing.
Okay, so mean drift, fighting the normalizer, and bulldozing neurons into dead zone. But the sources point out one more reason. It has to do with something everyone is obsessed with right now. Massive context windows. Like, people want models that can read entire novels, 100,000 words at once. Why does the bias break long context?
The fourth reason deals with length extrapolation blowup. The core engine of a transformer is the attention mechanism. Attention works by having every token compare itself to every other token in the sequence, using mathematical dot products. It's trying to find out which words are most relevant to each other.
So if the sentence has 2,000 words, it's doing millions of comparisons.
Right. Now, imagine what happens if the vectors being compared contain unvarying bias constants. When you take a dot product, you multiply the values and sum them up across all the dimensions. If both the query vector and the key vector contain the same constant bias across their dimensions, those constants get multiplied together over and over again.
Oh, no.
Yeah, it creates a systematic, artificially high baseline score in the attention matrix that has absolutely nothing to do with the semantic meaning of the words.
It's like having a microphone that naturally produces a low hum. If you amplify the audio enough, the hum drowns out the person actually speaking.
That's exactly it. And when you expand the sequence length from a standard 2,000 tokens to 32,000 or 100,000 tokens, the number of comparisons grows quadratically. This constant bias accumulation scales with the length. It quickly blows right past the numerical limits of the softmax function, which processes the attention scores.
And we know what happens when it hits the limit.
In BF16 precision, it triggers an instant NAND crash. The math literally explodes simply because the input text was too long.
So Google actually proved this in the Paul paper, right? By explicitly setting bias, false everywhere, removing it from linear layers, removing it from layer norms, from embeddings, they achieved a massive boost in training stability without losing any actual intelligence or generalization power. It's literal addition by subtraction.
It is a profound example of understanding the physical mechanics of the network and removing the exact component causing the turbulence.
But hold on, I have a fundamental question about this. If the AI optimizer, the underlying algorithm driving the learning, usually something like Adam W, if it's so incredibly smart,
Yeah.
why do we have to handhold it with hard-coded rules like bias? False. Why do we have to force it to use RMS norm? If bias is causing a massive drift, shouldn't the optimizer just look at the network, realize the bias is getting too big, and automatically learn to push it back down to zero?
That's a great question.
Like, why can't the model heal its own architecture?
It's a very deep philosophical and mechanical question.
Right.
Why can't a learning machine learn to stabilize itself? The answer exposes the fatal flaws of gradient descent. We have this tendency to anthropomorphize these models, to think of the optimizer as an omniscient intelligence guiding the network. But gradient descent is not a superintelligence with a global perspective. It's an incredibly rudimentary algorithm that is entirely greedy and completely nearsighted.
Greedy and nearsighted. Let's break that down. How does it actually navigate the math?
Picture the loss landscape, the mathematical terrain the model must navigate to lower its error, as a massive, jagged mountain range in millions of dimensions. Gradient descent is like a blindfolded man standing on that mountain, trying to find the lowest valley by only feeling the slope of the ground directly under his feet.
So he's just feeling the ground.
Right, exactly. Just feeling the slope under his feet. Furthermore, the optimizer only looks at the current batch of data. It doesn't see the whole data set at once.
It's just reacting to the few paragraphs of text it's looking at in that exact microsecond.
Precisely. Let's say we are at training step 10,000. If tweaking a bias upward by a fraction of a percent will artificially lower the loss on this specific batch by 0.001, the optimizer will happily do it. It will gorge on that tiny short-term gain. It wants the number to go down right now.
So it's utterly blind to the fact that this tiny tweak, when accumulated over 80 layers and hundreds of thousands of steps, is going to cause a catastrophic mean shift later on.
Exactly. It's walking right into a trap. By the time the consequence of that short-term action explodes into a loss spike 100,000 steps later, it's too late. The network has already fallen into the dead zones or it hit a NAND crash. The gradients are physically destroyed.
Wow.
The model has lost the signal it would need to execute a self-correction. It's like someone eating massive amounts of junk food every day. Locally, in the moment, they feel great, right up until the sudden heart attack. The optimizer fundamentally cannot plan for long-term physiological health.
That makes a lot of sense. But what about the weights themselves? Let's say we take away the RMS norm shield entirely. We let the network run raw. Couldn't the millions of parameter weights just naturally learn to balance themselves perfectly so the variance doesn't explode?
Mathematically, that requires the parameters to perform a perfect random walk on a microscopic razor's edge in high-dimensional space. Think about a deep network without norm layers. If every layer's weights update independently based on local gradients, probability theory dictates that the variance of the signal will naturally grow exponentially as it passes through the layers.
Okay.
So in order to learn to act like a norm layer, millions of independent parameters would have to miraculously update in perfect orthogonal synchronization at every single step just to keep the variance exactly at 1.0.
It's like throwing a billion dice and expecting them all to land on a 6 every single time you throw them.
And there's an even more brutal reality, which is the ultimate chicken and egg problem of deep learning. Let's indulge the theory that the optimizer could eventually learn to normalize itself over time. The tragic reality is it never gets the chance. When you initialize a fresh model, the weights are randomly assigned. In a 100-layer network without norm layers, the variance explodes so violently that during the very first forward pass step 1 of training, the numbers exceed 65,000, the model hits a NAND, and it crashes instantly.
It's literally brain death on day one.
Yeah.
It never survives long enough to actually learn how to be stable.
Exactly. Which brings us to a golden rule of modern AI architecture, a rule etched in blood by researchers who lost millions of dollars in compute. Never leave a problem for the optimizer to learn if you can solve it with a hard architectural constraint.
Oh, that's good.
The optimizer has enough work to do just trying to understand human language, logic, and reasoning. We shouldn't force it to also act as its own life support system. By physically removing the bias and hard-coding the norm layers into the structure, we free up 100% of the model's capacity to focus entirely on learning intelligence.
Okay, that makes perfect sense. The optimizer is blind, and the hardware causes nans when the numbers get too big.
Yeah.
But I want to try a massive thought experiment based on the research.
Okay, let's hear it.
What if we completely remove the physical limitations? Scenario 1. I give you infinite precision supercomputer, a magical machine where nans simply do not exist. It can calculate numbers up to 1 trillion decimal places without breaking a sweat. We remove the norm layers, we leave the bias in, we let the variance run wild. With infinite memory, can the model learn to converge and become intelligent?
It's a beautiful thought experiment because it forces us to separate hardware limits from mathematical limits. And the answer might disappoint people who think better hardware is the only path forward. The answer is no. It still absolutely fails to train a stable, intelligent LLM.
Wait, really? Even with infinite memory and no crashes, it still fails. Why?
Because the NAND crash is just a symptom, it's a fever. The actual underlying disease is mathematical chaos and the sheer annihilation of usable information during the forward pass. Even if your magical supercomputer never throws an error, the lost landscape itself physically degrades into what mathematicians call a chaotic or fractal terrain.
A fractal terrain. Paint that picture for me. What does that mean for the blindfolded man on the mountain?
Because we removed the norm layers, the signals traveling through the network are still undergoing massive exponential amplification. So a microscopic adjustment to a single weight in layer 1, say, changing it by 10 to the negative 50th power, gets multiplied and magnified 80 times. By the time that signal reaches the output layer, that incredibly tiny change alters the output by 10 to the positive 50th power.
So the sensitivity is completely blown out of proportion.
Exactly. The loss landscape is no longer a smooth bowl or a gentle valley that the optimizer can slide down. It becomes an infinite series of sheer cliffs and bottomless chasms. One tiny step left, and the loss shoots up 1,000,000 points. One tiny step right, and it plummets into a crevasse.
1,000,000 cliffs and valleys, right?
Right. And because of this fractal terrain, the optimizer experiences a phenomenon called functional gradient vanishing.
How could a gradient vanish if the computer has infinite precision?
Your magical computer can accurately calculate and store a gradient of 10 to the negative 50,000. It doesn't underflow to zero. The computer holds the number perfectly. But think about applying that incredibly tiny update to a weight that currently equals 1.0. When you subtract 10 to the negative 50,000 from 1.0, the physical change is meaningless.
Oh, I see.
The weight macroscopically does not move. You could run that supercomputer for 1 billion years, and the network would effectively remain frozen in place. It loses all statistical ability to navigate the space.
That is mind-blowing. Okay, so magical hardware doesn't fix the math. Let's try scenario 2. What if the fundamental problem is gradient descent itself, the blindfolded man? What if we throw out gradient descent and use a mature quantum computer?
Ooh.
Let's say we use quantum superposition and global probability sampling. The quantum computer can instantly view the entire lost landscape at once. No blindfold, no step-by-step walking, and just sample the global minimum. Can we train our unconstrained model then?
You're jumping straight to the absolute theoretical frontier of computational physics, using quantum machine learning, techniques like quantum Gibbs sampling, to entirely bypass the local minima trap. It's a brilliant concept. But again, the physics of the network fights back.
It still fails.
If we try to train this standard, deep, unconstrained transformer using global quantum sampling, it fails. And it fails because of a uniquely quantum mathematical disease known as barren plateaus.
Barren plateaus. That sounds incredibly ominous. What happens to the landscape?
It is the absolute nightmare of quantum machine learning. It has been mathematically proven that in a randomly parameterized deep quantum neural network that lacks strict structural constraints, as you scale up the size of the network, the energy landscape flattens out exponentially.
Flattened, like the cliffs and valleys just disappear.
Completely. In the classical world, you have the jagged fractal cliffs we just talked about. In the quantum world of barren plateaus, the entire multidimensional universe becomes perfectly, absolutely flat everywhere. The variance of the gradients drops mathematically to zero. The entire landscape is a featureless plane, except for a few microscopic, infinitely sharp needle points that represent the optimal solutions.
So instead of navigating a rugged mountain, the lost landscape turns into a perfectly flat desert the size of the galaxy, and the answer you're looking for is a single, specific grain of sand.
That is exactly it. And even with a quantum computer's ability to sample globally, trying to blindly sample that one needle point in an infinitely flat, multidimensional desert requires a sample size and an amount of time that radically exceeds the lifespan of the universe. Global sampling becomes a statistical impossibility.
Oh,
If we connect this to the bigger picture, both thought experiments prove the exact same profound truth. You cannot brute force a mathematically flawed architecture with better hardware or better optimization algorithms. The universe simply doesn't allow it.
the constraints are the feature, not the bug. The norm layers, the removal of the bias. They aren't compromises. They're the physical laws we must write into the network to force the mathematical landscape to have shape, to have navigable hills and valleys.
Precisely. Without the constraints, learning is physically impossible no matter what machine you run it on.
That is profound.
Mhm.
Okay, let's pivot to something you mentioned earlier. You said that the real disease isn't just numerical chaos, but the annihilation of information during the forward pass. This leads us directly to what the sources describe as the most dangerous, unseen phenomenon inside an LLM, a black hole called rank collapse. What exactly is rank collapse?
Rank collapse, or as it's sometimes called in the literature, token uniformity, is arguably the most terrifying thing that can happen to an LLM's brain because it happens completely silently. To really understand it, we need to visualize how a model processes text. When a model reads a sentence, it doesn't see words. It processes each word or token as a high-dimensional vector. Let's say it's a 40096-dimensional vector. The word apple has its own vibrant, distinct coordinates in this space. The word quantum has completely different distant coordinates.
They all have their own unique personality, their own distinct real estate in the mathematical space.
Right. In a mathematically healthy network, the matrix containing all these tokens has a high rank, which simply means the tokens are linearly independent and distinct from one another. But as the data moves through the layers of a transformer, specifically through the self-attention mechanism, a physical annihilation of that uniqueness begins to occur.
Oh.
If you let it run unchecked, by the time the data reaches layer 80, the distinct representations of apple and quantum are pulled together. They converge. They become mathematically identical. The matrix rank collapses from thousands of dimensions down to one.
Here's where it gets really interesting. I like to think of this as putting 100 vibrant, completely distinct paint colors into a high-speed blender. At first, you have distinct, beautiful swirls of red, blue, yellow, green. But if you just let the blender run and run, eventually everything turns into a uniform, muddy gray. The model can no longer tell the difference between apple and quantum mechanics because their mathematical colors have degraded into the exact same muddy gray.
That blender analogy perfectly describes token uniformity. And what's absolutely crucial to understand is why the transformer has this collapse gene built into its DNA. It isn't a bug in the code. It is a fundamental consequence of the self-attention mechanism itself.
Wait, self-attention, but that's the core of the whole model. That's the specific mechanism that makes transformers so powerful. The famous Google paper was literally called "Attention is All You Need." How is the engine the thing causing the collapse?
It is incredibly powerful for capturing context, but mathematically, the attention mechanism relies on the softmax function to turn similarities into percentages. And a matrix processed by softmax is what mathematicians call a row stochastic matrix.
Okay.
The values in each row sum perfectly to 1. And applying a row stochastic matrix acts as a contraction mapping. It is essentially computing a complex, weighted average. Every single time a layer performs self-attention, it pulls the token vectors slightly closer together in geometric space. It actively forces them to blend.
So it's constantly averaging them out.
Yes. And if you do this 80 times across 80 layers, you invoke a principle from probability theory known as Markov's Perron-Frobenius theorem. This theorem governs how state matrices in Markov chains converge over time.
Let's unpack the Perron-Frobenius theorem a bit, because that sounds pretty intense. What does it actually mandate?
Imagine a Markov chain as a series of lily pads and a frog jumping between them. The stochastic matrix tells you the probability of the frog moving from pad A to pad B. The Perron-Frobenius theorem essentially proves that if the frog keeps jumping long enough according to these probabilities, eventually the exact starting position of the frog ceases to matter.
Okay, a frog.
The system reaches a stationary state, an equilibrium where the probabilities smear out evenly across the network.
So, translating that back to our words.
It means that if you repeatedly multiply a set of vectors by a stochastic attention matrix, the theorem mathematically guarantees that all the distinct tokens will eventually converge to the exact same stationary vector. All the colors inevitably become the muddy gray.
So the very thing that makes the model smart connecting words to other words to understand context is governed by a mathematical law that is naturally trying to melt its brain into a single puddle. How do the architects fight a mathematical law? How do you stop the blender?
They fight it using the very structural components we discussed earlier. First, the residual connections. If attention is the blender, the residual connection is a separate pipe that bypasses the blender and constantly adds fresh, unblended paint from the previous layer directly back into the mix. It forcefully re-injects the original distinct identity of the token at every single step, fighting the averaging effect.
And what else?
The norm layers. If tokens are naturally contracting and pulling toward a central average, norm layers act as a violent spatial stretcher. After every attention block, the norm layer takes the clustered tokens and forcefully repels them away from the center, spreading them back out across the geometric sphere, restoring their variance.
So attention's a gravitational force trying to crush everything into a singularity, and residuals and norms are constantly fighting to push the universe back apart. It's an endless, violent tug of war happening inside the machine millions of times a second.
Precisely. And the intelligence of the model, its ability to actually reason and understand language, only exists in the delicate, precarious balance between those two opposing forces.
Okay, but I have a practical question here. Let's say the balance fails. The model undergoes rank collapse and gets dumb. If all the words turn to muddy gray, the loss function must absolutely skyrocket, right? The researchers watching the dashboard would see bright red warning lights letting them know the model's brain just melted.
And here is where the research drops an absolute bombshell. No, the loss can actually look completely perfect. You can have a model undergoing severe rank collapse, its internal semantic representations completely melted into a single dimension, and the training curve will show a beautifully low, smooth loss, completely tricking the researchers into thinking the model is learning perfectly.
Wait, how is that physically possible? If it doesn't know the difference between an apple and a quantum state, how is it correctly guessing the next word and lowering the loss? How is it passing the test?
It's passing the test by cheating.
Cheat?
It is a massive illusion driven by the final layer of the network, which is called the language model head, or LM head. This final layer is an absolutely massive linear matrix whose sole job is to project the hidden 4096 dimensional vectors back out into the human vocabulary of 100,000 distinct words. This LM head acts as an extreme, high-dimensional magnifying glass.
A magnifying glass looking at the muddy gray puddle.
Yes. Even if all the tokens have collapsed into a microscopic cone where they share 99.9% of the exact same coordinate values, they are technically still floating in a 4096 dimensional space. The LM head has so many parameters, literally millions of weights, that it has enough geometric flexibility to snake a hyperplane between those microscopic differences.
Wait, so it finds something.
It exploits infinitesimal random noise differences down to the 10th decimal place. It grabs onto a tiny 0.00001 difference and amplifies it wildly to output the correct word.
So the optimizer is lazy. It realizes that maintaining a complex, beautiful geometric mapping of the English language is hard work. Instead, it finds it easier to just collapse everything, huddle all the tokens into a tiny corner, and rely on surface-level statistical noise to guess the next word.
Exactly. The network degrades into what researchers call a pseudo-endogram. It acts like a broken, glorified hash lookup table. It's not learning deep grammar, logic, or worldly facts. It's just memorizing microscopic noise coordinates to trigger a specific sequence of outputs. We call this phenomenon shortcut learning.
That is wild. It's like a student whose brain has completely shut off during the lecture, but they memorize the exact microscopic scratch marks on the multiple-choice bubble sheet to know which answer is A, B, C, or D. They get an A+ on the practice test. But what happens when they graduate? What happens when this collapsed model faces real users in the real world?
It experiences what the literature calls brittle collapse. The model gets an A+ on the training text by cheating. But the second you give it zero-shot data, a prompt from a user that it has never seen before, or real-world text from a new domain, those microscopic noise coordinates shift.
The scratch marks change.
The scratch marks on the paper change. And because the model has no actual semantic understanding of the concepts to fall back on, the LM head's extreme magnifying glass amplifies the wrong noise. The model suddenly spews complete gibberish, hallucinates wildly, or gets stuck in infinite repeating loops, just outputting the forever.
Because it's trying to find the safety of the muddy gray.
Wow.
But the coordinates moved and it's completely lost. This is a brilliant distinction. Classic overfitting is when a model has a super complex brain and memorizes the training data too perfectly, like a student memorizing the textbook word for word. But this ring collapse is microscopic overfitting. The brain physically melted into a single dimension, but the final output layer is pulling off a massive mathematical magic trick to hide the brain damage.
That is a perfect summation. Classic overfitting means the brain is too complex. Rank collapse means the brain has physically lost its structural capacity.
Okay, so we know attention is the blender causing this collapse. We know residuals and norms fight it. But there was another massive weapon the architecture uses to rescue the distinctness of the tokens, and it takes up about 2/3 of the entire parameter count of the model.
Right.
I'm talking about the feed-forward networks, the FFNs. How exactly does an FFN work mathematically to save the model from the blender?
The feed-forward network sits right after the attention block in every single layer. Its mathematical structure is a fascinating breathing mechanism. It consists of three distinct parts. First, a matrix we'll call W1. This is the expansion matrix. It takes a 4096-dimensional token and blows it up, expanding it to a massive 16,384 dimensions.
Okay.
Next, an activation function like ReLU or SWIGILO is applied across this massive new space. Finally, a second matrix, W2, compresses that 16,384 dimensional vector back down to 4096 dimensions so it can be added back to the residual stream.
It breathes in, expanding to 16K, and breathes out, compressing to 4K. But wait, you lost me there. Why would expanding the dimensions help if we just shrink them back down again a microsecond later? Why not just apply the activation function at the normal 4096 dimensions? Why spend 8 times the computational cost, billions of extra calculations, just to inflate it only to shrink it?
It's all about a foundational concept in machine learning known as Cover's theorem. Cover's theorem states that casting complex, entangled patterns into a high-dimensional space non-linearly makes those patterns more likely to be linearly separable.
Okay, let's break that down for the listener. What does it mean for words to be linearly separable?
Think about the 4096 dimensions as a very crowded room. Words with multiple meanings, complex grammatical rules, abstract concepts, they're all tangled up together. If you try to draw a straight, flat line through the room to separate the fruit meaning of the word apple from the tech company meaning of apple, you can't. The data points are too entangled. But when W1 expands the space to 16,384 dimensions, it pulls everything apart. It creates massive memory slots. Researchers believe this acts as a key-value storage system. The 16,384 dimensions provide enough physical geometric space to distinctly map out tens of thousands of different semantic concepts without them overlapping.
And we have to do it before the activation function because of what the activation function actually does.
Yeah.
If we used a ReLU activation function right at 4096 dimensions, ReLU kills all negative numbers. It sets roughly 50% of your activations to 0.
Exactly.
If you do that at 4096, you only have 2,000 surviving dimensions. You choke the network. It's an information bottleneck. But if you blow it up to 16,384 first, and ReLU kills half of them, you still have 8,000 surviving rich, highly specific dimensions to compress back down.
Exactly. You provide the activation function a massive canvas to work on, so you avoid the information bottleneck entirely.
That is an incredible aha moment. So the activation function adds information by creating these nonlinear dimensions that makes the model smarter.
This raises an important question and exposes a beautiful, counterintuitive paradox in information theory. The activation function does not add information. Physically, mathematically, it destroys information.
Wait. It destroys it.
Remember what the ReLU function physically does. If an input is -5, the output is set to 0. If the input is -100, the output is set to 0. It intentionally deletes the difference between -5 and -100. It irreversibly destroys physical data. According to the data processing inequality in information theory, you can never increase the total amount of information by processing it.
Then how does destroying information make the model smarter? How does it help Cover's theorem separate the words?
Because true intelligence requires selective forgetting. The raw data of human language is full of noise, redundant correlations, and irrelevant context. The linear expansion, W1, just stretches that noise out, but the activation function acts as a sculptor's chisel. By selectively deleting physical noise-turning irrelevant negative values to absolute 0, it creates massive semantic purity. It throws away the physical data it doesn't need, which makes the semantic data that survives incredibly crisp and linearly separable.
Oh, I love that. I'm imagining taking a flat 2D piece of paper with a messy, tangled drawing on it and hovering it in 3D space. That's the linear expansion. It's still just a flat piece of paper. The topology hasn't fundamentally changed,
Right.
but the activation function is like an origami artist.
Yes, perfect.
It takes that paper and starts aggressively folding it and cutting away pieces in the 3D space. It creates these complex 3D ridges and valleys.
Yeah.
Now, with a single straight cut hyperplane, you can separate complex ideas that were totally tangled together on the flat paper. It destroys paper to create shape.
That is a phenomenal visual. The activation function folds the space. And W2 is the process of shining a light on that complex 3D origami shape and casting its distinct, highly complex shadow back down into the 4096 dimensional residual stream. That complex shadow is what prevents rank collapse. The FFN forcefully injects distinct, highly separated individuality back into the tokens.
Okay, so the FFN expands from 4096 to 16,384, cuts the origami and compresses back to 4096. What about the attention blocks? We know they act like a blender, but what is their dimensional rhythm?
The attention mechanism does the exact opposite of the FFN. It compresses, then expands. When a 4096 dimensional token enters the attention block, it is immediately chopped up into pieces. In a standard model architecture, it might be divided into 32 distinct heads.
Okay.
4096 divided by 32 means each head only operates in a tiny 128-dimensional space. The attention calculation, the blending and comparing happens entirely in that squeezed 128-dimensional space. Then, all 32 heads are concatenated, stitched back together, and projected back out as a single 4096-dimensional vector.
Hold on. Why? If 40 and 96 dimensions hold all the rich semantic detail, why chop it down to a tiny 128-dimensional space to compare to other words? Why not just do one massive 49.6-dimensional attention head? Wouldn't that retain way more info?
That's a very logical question, but mathematically, a single massive head is a terrible idea for two critical engineering reasons. First is what we can call the softmax saturation problem.
Softmax saturation, how does that break the model?
Attention works by taking the dot product of two vectors to see how similar they are. When you take the dot product of two massive 4096-dimensional vectors, you are summing up 4096 multiplication results. The resulting number can be astronomically huge. When you feed that massive number into the softmax function, which is designed to turn scores into percentages, softmax becomes hypersaturated.
A good analogy here might be an audio microphone clipping. If you have a room full of people talking, a good microphone picks up everyone. But if one person screams directly into the mic, the signal overloads. The microphone maxes out at 1.0, it clips, and because it's maxed out, it cannot hear any of the other quiet voices in the room.
Exactly. Softmax turns the largest dot product into exactly 1.0 and forces every other number to exactly 0. The model hyper-focuses on one single word and completely ignores the rest of the entire paragraph. The gradient vanishes instantly. By squeezing the vectors down to 128 dimensions, the dot products stay small and healthy, allowing softmax to act like a properly tuned microphone, distributing attention smoothly across multiple words.
And what is the second reason for chopping it into 32 heads?
Diversity of thought. If you have one massive head, the model can only look for one single type of relationship at a time. But by chopping it into 32 small heads, they act as 32 specialized squads. Head 1 might look purely for nouns. Head 2 tracks emotional sentiment. Head 3 tracks subject-verb agreement.
I see.
In their compressed 128-dimensional spaces, each head is forced to hyper-focus on one specific type of relationship. When you stitch them back together, you get a wonderfully diverse, multifaceted understanding of the sentence.
So if we step back and look at the whole layer, we see the true rhythm of the transformer, the heartbeat of the AI. Attention compresses the data into specialized squads to find relationships across different tokens, sacrificing their individuality to understand the broader context. Then, the FFN expands the data to consult vast internal knowledge banks, folding the space to restore and enhance their individuality, compress to connect, expand to individualize, over and over, for 80 layers.
That is the beautiful, brutal choreography of a large language model. And all of these mechanisms expanding, compressing, the norm layers repelling tokens, the activation functions folding space, they are ultimately all fighting a unified war. They're fighting to protect one single ultimate metric that defines the true health and intelligence of an AI.
The grand finale metric. Let's hear it.
It is called effective rank, or E-rank. It is the countermetric to rank collapse.
How is it different from the regular absolute matrix rank we talked about earlier?
Absolute rank is just a physical count of the dimensions. If the vector is 4096 dimensions long, the absolute rank ceiling is 4096. But as we saw with the cheating LM head, you can have a model where 4095 dimensions are filled with microscopic, useless noise, and one single dimension is hoarding 99% of the actual semantic energy. The absolute rank is technically 4096, but the mathematical space is crushed. It's anisotropic. It has effectively collapsed.
So effective rank exposes the cheat. How is it calculated? Because I know the research mentions Shannon entropy.
Yes, it calculates the Shannon entropy of the singular values of the matrix. Let's unpack Shannon entropy. In physics, entropy is a measure of disorder. But in information theory, Claude Shannon defined entropy as a measure of surprise, or how evenly information is distributed.
Okay, let's use an analogy. Imagine the 4096 dimensions are a plastic ice cube tray with 4096 little slots.
Perfect. If you pour water into the tray and it spreads evenly, filling every single slot perfectly, that system has high entropy. The energy is perfectly distributed. But if you tip the tray and all the water pools into one single giant block in the corner, leaving 40 and 95 slots completely bone dry, that system has low entropy.
And applying that to the tokens.
If one dimension hoards all the mathematical energy, if all the water is in one slot, the entropy drops to near zero, and the effective rank collapses to 1. The model is brain dead, just using one feature to guess words. But if the energy is spread evenly, perfectly balanced across all 4096 dimensions, the ice cube tray is full, the space is isotropic, the effective rank is high.
And a high effective rank means the model is building robust, healthy, linear separability. It has a massive, wide-open canvas to draw its complex conclusions about language and reasoning. That is true intelligence, not just microscopic overfitting.
Exactly. And because preserving effective rank is the absolute holy grail of training, AI engineers have built an entire toolbox of ingenious mathematical tricks just to artificially inflate it and protect it. We already mentioned SWIGL-U, which uses a dual stream gate to prevent neuron death, keeping more dimensions active than standard real U.
Right. But what else is in this toolbox? The sources list a few other incredibly specific mechanisms: QK-norm, Rho-P, isotropic regularization. Let's take the time to really unpack how these work, because this is where the cutting-edge engineering lies. Let's start with QK-norm.
QK-norm, or query key normalization. In massive models like Google's 22B Vision Language Transformer, they found that even with 128-dimensional heads, the dot products could still grow too large and trigger that microphone clipping we talked about. So they apply a strict layer norm specifically to the querying key vectors right before they are multiplied in the attention block.
What does that do geometrically?
It artificially forces all the token vectors to sit on the surface of a hypersphere. By enforcing a strict geometry, it puts a hard mathematical cap on how large the dot product can physically get. It acts as an absolute safeguard, protecting the softmax from saturating, which keeps the attention dispersed and protects the effective rank.
Forcing them onto a sphere. That is so elegant. Now, what about Rho-B? What do we position embedding? This one is famous because almost every modern model uses it. How does it work?
To understand Rho-P, you have to understand that the transformer architecture naturally has no concept of order. It treats a sentence as a bag of words. To fix this, older models used absolute positional embeddings. They literally just added a static signal, like a sine wave, to the word vector to say, I am in position 3. But simply adding numbers artificially skews the mean, which we know causes rank collapse.
So Rho-P doesn't add anything, it rotates.
Exactly. Imagine the word vector as an arrow pointing outward on a clock face. Instead of adding a number to the arrow, Rho-P physically twists the arrow by a specific angle. Token 1 might be twisted 10 degrees. Token 2 is twisted 20 degrees. Token 3 is twisted 30 degrees.
Oh, I see. And because attention relies on the dot product, which measures the alignment of two arrows, the angle heavily influences the score.
Yes. Two words will have a high attention score if their inherent semantic meaning is similar, and if their twisted angles align properly, representing relative distance. But geometrically, because Rho-P forces vectors in different positions into entirely different rotational planes, they physically cannot perfectly merge together during the attention blender phase. The geometric twist actively forces the tokens apart, artificially propping the rank open.
It twists them so they physically can't fit into the blender properly. That is absolute genius.
And finally, the sources mention explicit isotropic regularization. This is perhaps the most direct intervention. They literally alter the foundational loss function. The optimizer is trying to lower the loss. So engineers inject a new penalty directly into the loss calculation. During training, the system constantly monitors the cosine similarities between all the tokens.
It's checking to see if they're clustering into the muddy gray puddle.
Exactly. If it detects that the tokens are getting too similar, the loss function artificially spikes. It actively punishes the model. It's like a wrist slap. The optimizer wants the loss to go down, so it is mathematically forced to push the tokens apart to avoid the penalty. It's a brute force method of enforcing isotropy.
Wow. It is a constant, desperate war against physics. Let's recap this incredible journey. We started with the foundational realization that at massive scales, a single anomaly can cause a numerical storm that destroys millions of dollars in compute. We saw how the humble bias term acts as a bulldozer, shifting the mean and breaking the normalizers until researchers realized they just had to rip it out of the math entirely.
We saw that we cannot rely on the optimizer to save itself. It is a blind man on a jagged mountain, completely incapable of planning for the structural health of the network. We must impose strict architectural laws.
We looked deeply into the black hole of rank collapse, understanding how the Perron-Frobenius theorem dictates that the attention blender will naturally try to turn all distinct concepts into a muddy gray puddle. We exposed the illusion of low loss, where the model cheats by micro-overfitting that puddle using the massive LM head. And finally, we saw the cure. The breathing rhythm of the FFN, expanding to 16,000 dimensions so the origami artist of the activation function can cut away the noise, and the intricate geometries of rope E and QK norm working to restore the effective rank of the system. It is absolutely mind-blowing how much violence and counter-violence is happening inside these matrices just to output a simple, coherent sentence.
It truly is a marvel of mathematical engineering. It's the ultimate act of forcing order onto inherent chaos.
Well, we've seen how LLMs constantly fight this rank collapse, this natural gravitational tendency to blend all distinct, vibrant ideas into one muddy, easy-to-process average. And, as we wrap up, taking a step back from the massive server farms and the high-dimensional math, it makes you wonder, is human learning much different? When we consume too much uniform information, when we isolate ourselves in comfortable echo chambers that constantly validate our existing beliefs, do our own mental models suffer a kind of cognitive rank collapse? When was the last time you let an opposing viewpoint act as a normalizer to stretch your perspective? What are the residual connections in your life? What are the unique experiences, the challenging books, the diverse viewpoints that are actively keeping your thinking distinct, vibrant, and high-dimensional? Think about that. Thank you for joining us on The Deep Dive. Catch you next time.